2022 logic design. And okay, this allow me to share also my desktop. All right, so this time it's about time now to
Teacher,
have our chapter 2. Yes, who's that one? Yes, please. Tell me.
you not call me on.
Said? Said
So
Salim?
what problem of these channels?
Khalid? Any problem from your connection?
Not connection, teacher. There are many channels in the chat.
There are many channels.
Teacher,
Technically,
Yeah.
technically everyone can create a channel, but the moment I'm not the one who created, of course that is not the official channel. This is only one channel. Just now I sit here and then I make the channel. I have seen that one time. I have seen that one time. When I open my MS Team, one channel has been created already. Only the person that can create the channel is most likely another teacher, or most likely if you have a chance to create your channel, but I don't think so. I don't think so. Anyone's doing that one is you have to join to the other channel where you can see me actual, right? You won't be expending your 2 hours
Yes,
there.
teacher. Join the before coming here.
Yes, I saw that one. I saw that one. Someone create another channel. I don't know what happened, and only normally teachers can only create that channel, but could be someone else. But in case that
Teacher, did
might
you
happen, yes, Khalid.
check my
In
name,
case,
please?
okay, 1 second, Khalid. Khalid. Okay, Khalid Ahmed.
Teacher, I'm
Okay,
the lead teacher.
no problem. Who's that? Can you mention your name again? Khalid is now present.
Great teacher.
Hmm? What's your name?
Great, great,
I'm sorry, once again.
great teacher.
Okay, okay, yes. Light. Okay, sorry, light, because your voice is not.
teacher, also my name.
Problem, teacher.
Okay, and who is that? Please mention your name.
Said Salam, teacher.
Said Salim. Okay, Said
Last one.
Salim.
Teacher, also me, show.
Okay, show. 1 minute. Said Salim. Said Salim Hussein, no? Said Salim
No, teacher,
Hussein.
Said Salam Al-Kathiri.
Said Salim Al-Katiri. One second. Oh, okay. Said Salim. Said Salim. Kalas already. I already marked you present though. Wait. Shok. Shok Abdul Rahman. Okay, present. Don't worry, I will mark attendance 1 second later, right? Don't worry. This is just for my reference on my Excel sheet. But the official, just stay put, of course, because the CIMS enter later will be done. Okay, so this time, well, good afternoon. And I want you to know that the chapter 2 of our PowerPoint presentation is now available in our e-learning. Now I already downloaded, but anyhow, we can also use our ITNT course handouts that the chapter 2 is also mentioned there. Okay, so this time, it's about time now to learn this very interesting part of the logic design. It's basically start the essence of logic design subject is coming from this chapter. I'm not saying that chapter 1 is not important because it's a part of digital electronics. In chapter 2 now, please stick with me, and if you really wanted to apply this in the practical side of logic design, this is the best time for you to listen and understand all the topics that I will be discussing within this chapter, right? Because this chapter 2 we're talking about now about logic gates. From your subject itself is logic design, but it came purely on the logic gates. This is what we are dealing with until the end of the semester, completing our outcomes. Okay, this logic gates comes with another topic, which is Boolean algebra. Then again, you might be thinking, oh, Boolean algebra, it's again mathematics. Not much though, because Boolean algebra is just like an expression that how we can understand how the logic gates works, right? So that's why we have logic gates and Boolean algebra. That's combined together, basically. If I tell you one logic gate, it comes with the Boolean algebra, right? So this is how it goes. If you want to design a logic gates, I might give you the Boolean algebra, or vice versa. If I show you the logic gate, you must know the Boolean algebra. It's just like an expression that might be suitable for you on designing and simulating a typical logic circuits. Okay, now, without further ado, we could just now straight away from this session. The objective of this chapter is, of course, we will be having introductions of logic gates, and you will find this one with the different logic basic gates, by the way, and eventually we will see some not basic but some combinational gates that they produce another new gates. And after that one, we will also learn the Boolean expression that makes kind of literals or variables, combine them together in such a way we could apply that one also in a logic circuits. And with that one, we are also learning the truth tables of each of the Boolean expression or maybe logic gates. And eventually, by the way, the logic gates comes with some illustrations or diagrams, or maybe we call that one a symbol. If you see that particular logic gate symbol, you know already what's the name and what's the function of this and how it works in logic design, right? And eventually, maybe the last part of our chapter is we will be dealing with combinations of these basic gates. So it's mentioned there that those basic gates are only, or, and not. So normally, at the end of this chapter, you will see that we will combine them in one circuit or in one design. Okay, so this is chapter 2. And we can just give a straight introduction on this logic gates, because what we have learned on chapter 1 is still pretty much carry on in chapter 2, because we are still dealing with binary logic here. Right, so we know already the binary numbers, hexadecimal, decimal numbers, and we also come to know how to convert them. We also find out that we can perform arithmetic binary numbers, or by performing subtraction literally, but we're doing it in a different fashion, which is addition of binary, something like that, using complements, right? You have seen that one. Now, what is the use of this binary logic now here in our logic on this chapter 2 particularly? Come to think of 0 and 1 is just an equivalent of turning on and off the switch. If I move or if I turn on the switch, the bulb will lit, of course. Vice versa, if I switch it off, of course, the bulb will not turn on, or it will turn off as well. This is considering one of the example of logic that these zeros and one might represent in a human kind of understanding, because literally that on and off is like 0 and 1. On is 1, I'm sorry, off is 0. We can also use that one as true or false, right? We can also use that one as true or false. We can represent true as 1 in binary logic. We can represent false as 0 in binary logic. Okay, think of this kind of situation. If we are now learning logic design, we just barely using these zeros and 1. Just like I said, it's just like a typical switch. Or maybe it's just like a true or false condition. In this case, we do have also some expressions eventually that we know that the light is equals to switch. It might be turning on if we do some movements over there. That's why I can say that down off, false, 0 are all the same output. Or pretty much maybe the other way around. Up, on, true are all equivalent to 1 when it comes to digital electronics or digital design. So imagine this one. If you made that statement light equals to switch and the bulb and the power will be also depends on the output. And that makes your statement. What we call that one as a logical expression. Later, this logical expression will become specifically as a Boolean expression now. Boolean in a sense, why? If you remember, or maybe some of you have taken already programming, Boolean is like, it's only between zeros or only normally between true or false, the Boolean. So we can assign true or false in Boolean. You can assign yes or no in Boolean. Yeah, missing that one, no? It should be having also yes or no. And similarly also that yes is 1 and no is 0. And eventually this expression will become a Boolean expression. We will see that one later once that we are now touching one logic gate along with his or her partner of expression. And now this time, we will not use on and off for now. We will not use yes or no or true or false. But for now, we will make use of specific functions that this logical circuit will represent them as one image, one picture, or one symbol, or one function itself. And what are those? We will name that one as an, or, not. Okay, remember those three, and, or, and not. Each of these specific functions might be having specific symbols later, so that you will clearly define. If you see that symbol, you know already what's the function of it. If you see the or symbol, you already understand, oh, I know how to this or functions works in digital electronics. And you find also that illustration of that or diagram of that not is basically very clearly defined, that you know that this is the function. So this is just giving you some introduction of logic gates. We know all of these things are all connected each other. But basically now, if we study the real basic gates now, this basic gates is basically your building blocks of a certain computer's architecture, basically. Most of our mobile devices, all the running electronics around us are all made up of logic gates. This headphone, my smartphone, the keyboard, the CPU, this monitor in front of me, the webcam in front of me. Every electronic devices, most likely they have this logic gate because they are the building blocks of this system, or let's say it's a hardware. So these building blocks, we can say that these are the logical gates, or just say it as gates. You know what is a gate is, right? So if you use that gate in English, it's just like your fence that will protect your house, pretty much. You put a fence within the camel, but there will be a gate that will open and close. So pretty much the same. That's why they made that one as gate, because logic gates works the same thing like that, like a door. You can open and you can close. I will show you why they made that name, because it's like an on and off, like a switch, an on and off, right? If you open it, it's like a loose connection. You don't have a power running on that line. If you close it, there will be a line connecting. But this gate is usually now exactly what we're using is they have basically one input and output. Only the question is that makes them different is, if we're only talking about gates, the input is most likely sometimes more than one input, or maybe one gate is only one input. It depends on the gate. And when it comes to output, if we're only talking about basic gates, all of them are only having one output. So a gate is basically generates this kind of constructed diodes and resistor. Oh, we are not engineering students at the moment. When I study this logic design, I have also electronics subject separate. And basically my teachers who teaching this electronics subject, they're talking about more on transistors, resistor. But here in logic design, we don't talk about that one at the moment because we are pretty much only using the symbols or diagrams that later we will come to learn. Because if you really want to go to engineering when it comes to electronics, you really needs to know how these gates have been constructed, by what components inside this one. Actually, those are transistors and resistors, right? These input and output values are, we call that one as logical values. Just like I said, it could be true or false. Okay, it's only between these logic inputs, those values might be true or false. But in the computer architecture, that true or false it's only between 0 and 1. And that makes sense. So false is 0 and 1 is true. That's it. This is only the digital electronics know or understand because this is the way they communicate. But in the human understanding, this is the equivalent as true or false, as fairly your input equivalent values. Basically, one of the popular application of gates are, other than, of course, computer architecture, these gates are basically like, it's an actual, like it's a switch actually. It's just like a switch. That this gate has no memory, but it depends on your input. Whatever you input it, or whatever you switch on and off, the value will immediately come out. That is basically the use of a gate, right? That's why they name it as a gate. So if someone is coming in, someone should pass through, or otherwise, someone is coming in, you don't want to let him go out there unless the other input will be there. So there will be a combination. Later, also we will come to know the Boolean functions. For now, we don't see the picture yet, what is a gate, and how the gates looks like, and what are these different basic gates. Knowing that we know already what is the gates, logic gates, each one of the logic gates comes with their respective Boolean functions. Always remember that one. Each and every gates comes with their respective Boolean functions. And these functions, we're going to perform them as they are like a formula, pretty much, like a formula, because they will going to use a set of variables. And those variables, we call that one as Boolean variables. Just like I said, it might be yes or no, or true or false. So which means those Boolean functions will take about 2 inputs maximum, or maybe 1 input minimum, depends on the gates, right? Because we have gates that comes with 2 inputs and gates that comes with 1 input as well, but all their output are 1. And later, this Boolean function, so that we could understand how the gates will work, we will use some variables, just like this one. If we have 2 inputs, we have A and B. Input 1, maybe I will assign A. Input B, I will assign B. And of course, what about the output, teacher? Oh, no problem. I can just assign any letter, or F, or function, or small letter F, just like this one now. F, open and close parenthesis, A, capital A, comma B. If you see this kind of expression, that is already actually almost, you're defining now that you have a function and you have assigned the variables for those inputs, which are A and B respectively. So which means now, by this performing this kind of task, you're doing actually literally a Boolean function already, but you haven't identified first, by the way, what are the inputs there. Only it will be complete when you assign completely the combination of the binary numbers or binary bits between A and B. Oh, again, I will go back to chapter 1. If you have two variables, how many possible combinations you might be getting in your two variable with the 2 raised to n?
4.
Very good. I never expected that one, that someone will going to answer that one. Yes, 4. Very good. Because those are 0, 0, 0, 1, 1, 0, and 1, 1. Quite the basic one though, right? So which means now you know already this combination. What you're doing is specifically is a Boolean functions already. Take note that those 0, 0, 0, 1, 1, 0, and 1, 1 can be also assigned like a true, true, false, 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 true, true, false, or false, false. It depends, or on and off. By the way, no, in lab, before the pandemic, actually, my students are doing this one in the lab. Those zeros and one are basically on and off switches only, right? So which means if you on, that is 1. If you off, that is 0. But at least now you understand what is a Boolean function. First was Boolean logic gates. Second, Boolean functions. By the way, you're not seeing the picture. What is the logic gates yet? Huh? Second, Boolean functions is pretty much like an expression based on your input and output. The third one is a truth table. And what is this truth table is all about? Why do we have truth table? Truth table will prove that your Boolean function matches the way the Boolean function should function. It should matches on your truth table. It's just like saying you put all your inputs and outputs in the table. If you simulate them with some variation of inputs, what will be the output? But take note, the Boolean functions depends on the functions. The truth table, whatever the function you have given in the Boolean function, it should show there in the truth table, just like this one. I'm not saying this is specifically in one gate, because you haven't seen yet the gate and the Boolean function. What's the truth table said is showing the inputs and output, which the Boolean function says that you have two variables. And just like I asked, no, how many possible combination of 2 raised to n of the two variables? 4. 0, 0, 0, 1, 1, 0, 1, 1. So those are combination of input that we have labeled it A and B. Now the challenging part here is the output. I said, right, minimum is 1 input. It so happened that this is 2 inputs. And normally minimum maximum output is only 1. That's why only 1 column is there. But this and is actually depends on the function of the Boolean expression. Because later on, this may be or, this may be not, or this may be and. So at least these are the output. We will go there one by one. Just only, I'm explaining what are the things that you might be encountering if we started learning now the specific Boolean, logic, the basic gates. Right? Because this Boolean expression eventually, it will combine all the expression. And when you simplify it using mathematics, actually, and substitute the value of 0 and 1 within that expression, it's the same. It will come on your truth table. Or even you do it vice versa. You got the truth table, you want to generate the Boolean expression, you can also do it. And the best thing with this, you can draw now the logic circuit. We know already these 3, but we haven't even seen how we put them all together. But this is the first time now knowing that this, if I mention logic gates, there will be a gates, there will be Boolean function, there will be a truth table, and there will be a Boolean expression. 4 information that I have introduced to you. And those 4 information, if I give you one gate, all of them has those 4 informations. You never know, maybe it's a picture, a diagram, a symbol, an arithmetic operator, or just barely a table, or maybe the other one is just like an algebraic expression. Now we have to learn now that we have 3 basic gates. And these three basic gates, just like I said, is only between these three and or and gate, and gate or not gate. I'm sorry. Assuming that you know already the inputs, but in the digital world, these are basically 0 and 1. But if you are in the lab, actually, or doing the simulation from our Logic Sim, by the way, you will be having a software performing some lab experiment later on. We can identify that one maybe a 0 volts or just a low volt or low as an input. The other one is a 5 volts or high. But in the digital world, actually, it's just only zeros and one. But if you're performing it in a Logic Simulator software, or maybe you are in the lab, electronics lab, performing it with a digital electronic board, this is what you are seeing, low, high, 0 or 5 volts. Okay, so don't be confused on this. If all 0 and low are all 0 in binary, 5 volts and high is equivalent to 1 in binary. Just like I said, gate has only one output signal. But regarding the input, it depends. Actually, the OR gate comes with 2 inputs. The AND gate has minimum 2 inputs. But we can customize that one even. And later on, it could have a multiple more than 2 inputs later. But at least we know that it has only one output signal. This operation of the gate can be defined in the truth table. Later, we will see, and each Boolean algebra represent those Boolean functions. Number 1 gate that you are now learning is AND gate. Okay, this is going to be your first ever gate that you're now seeing at the moment. And eventually, we will use this one in design and so many things that we will going to use this upon learning so many topics in logic design subject actually. And this would be your first ever gate that you're now seeing. I was expecting it would be an OR gate, but doesn't matter. Anyhow, we have 3 basic gates. So let's start with an AND gate. An AND gate looks like this. Straightforward, it looks like this symbol. You're seeing already in my slide. A symbol is like kind of cylindrical, right? But there's a curve there. But you can see now that it has 2 lines coming in. Those are inputs, which is assigned A and B. And the output was assigned as Y. Actually, variables doesn't matter. You can assign any letters as you wish, as long as you know the function of that particular gate. Knowing this symbol of an AND gate, you should know the function of this. And you will find it there at the bottom. Y equals to AB. Y equals to AB. Literally, this logical is an operator. In programming, actually, A and B. Actually, that is Y equals to A and B. Or maybe in mathematics, we just use A times B. A multiplied by B. But it's better to use the logical AND because AND is also considered as an operator. This is his function. So the moment that you know already the function, you can now represent a truth table out of that. Of course, as you know it has 2 inputs. The truth table assigns the variables there. The first 2 columns are your inputs. And with the 2 inputs, binary equivalent combination will be 4, which is 0, 0, 0, 1, 1, 0, 1, 1. Maybe your output will still be empty, but the moment you know that this truth table is all about AND gate, you just use the function there, y equals to AB. It's just like a multiplication, like what you have learned in arithmetic operation of multiplication of binary. 0 and 0 literally is 0 times 0, something like that is 0. 0 and 1 is 0, just like 0 times 1 is 0. 1 and 0 is like 1 times 0 is 0. And 1 and 1 is like 1 times 1 is 1. So this is the most important. Once that you see that symbol, you should know already the function immediately. And out of that function, you can come across with a truth table equivalent because you're pertaining to that logical AND that comes with the AND gate. All right? So this is the complete package. First is, actually it's four. First is the symbol of the logic gate. Second is the function, is AND function, is like multiplication. Third is the Boolean expression. Teacher, where's the Boolean expression? Y equals to AB. That's the Boolean expression now. Fourth one is the truth table that comes with input and output. Of course, the output is based on the Boolean function. Teacher, what is the Boolean function? It's AND. Pretty much like multiplication. Okay? Now, let's move to another version of AND gate. Now, teacher, you told us that's only coming with 2 inputs. So how come this one is coming 3 inputs now? That's why we have so many variation, but it's only highlighted that a typical gate has only 1 output. But I'm not saying that all the time it should be 2 inputs, one input. It depends on the property of that gate. But this example is basically, it has also kind of 3 inputs. Basically, there's also 4 output, 5 output. Depends, 5 inputs. But this time, the symbol pretty much changed because it added 1 more input there. Before you have only A and B. So, which means you are obliged to assign 1 more variable there, which now becomes A, B, C. Now, my next question is, what if you have 3 possible inputs, and what would be your possible combination? How many? How many possible combination? 8. Teacher, why 8? That is a 2 raised to n. That comes with the 2 raised to 3. Of course, 0, 0, 0 is included. Is equivalent to 0. 0, 0, 1 is second input. 0, 0, 0, 1, 0 is equivalent to 2, by the way. 0, 1, 1 is equivalent to 3 in decimal. 1, 0, 0 is equivalent to 4 in decimal. 1, 0, 1 is equivalent to 5 in decimal. 1, 1, 0 is equivalent to 6 in decimal. And 1, 1, 1 is 4 plus 2 plus 1 is 7. It's all 8. That includes 0, 0, 0. So that makes sense now. Since you know already how you apply what you have learned in number system with the magic of formula of 2 raised to n, you will come across with those truth table combinations. Because the inputs there, it depends on the number of variables, of course. And we'll just assign them 0 and 1. Now, of course, if the inputs is changed and it's not the same with the 2 inputs of AND gate, of course, your Boolean function will also must be changed. And you can see that the Boolean function there is f, a, comma, b, comma, c. And literally, this is about AND gate. It's just like, again, it's a multiplication. A times b times c. Or we say it in logic operator, A and B and C, which is basically it's a multiplication properties, pretty much. And getting the truth table is much more straightforward because we know that any multiplier of 0 will be definitely be 0. So that's why you're seeing now the output here are all 0 except only for 1. Because and a 1 and 1 and 1 are 1, but the rest will be 0. Just like you multiplied 0 times 0 times 0 is 0. 0 times 0 times 1 is 0 because you still have 0 there. 1 times 0 times 0 is still 0. 1 times 1 times 0 is also 0. Only we got only 1 is for 1 and 1 and 1. And you have written there, maybe I put here f if that is the final function. Right, but in the truth table, it could be also assigned or labeled that one as the function itself. There's a typical multiplication. It's there, oh? Right? A typical multiplication of binary. So there's no limit of number of inputs, to tell you frankly. It depends on the design, on the property of the gate. But as long as we know already that it would be having a single output. 1 second. Sorry for that. I'm getting some calls. Okay, so we'll just move on to another what do you call this one? Picture of a digital logic gates. I forgot to bring one of those, but in next meeting I will bring one of these IC. Okay, this is actually the actual package of of electronic devices, particularly in integrated circuits that holds those gates. And you are seeing basically maybe it's like a color black one, rectangular shape that comes with the pins. And some notches are there, and those pins are basically labeled from 1 to 7 or 8 to 14, something like that. It depends on number of pins. This integrated circuit are basically, they are embedding those logic gates inside. That depends that they might be giving some code on that IC, right? And it could be only be manufactured through, of course, some integrated circuit factory that they can only produce this kind of facility because they have this technology. And later on, they will use these chips. This is what they call chips, by the way, no? Those chips that we are seeing somewhere in your motherboard or in your smartphone devices, but probably it might be not the same size though, maybe in different shapes, most likely maybe some of which are already in square type, but it's very small one. Imagine that one, that a typical AND gate is basically a 7408. So this is the code of a typical 7408, meaning this is a quad, two inputs AND gate. Teacher, what is quad? 4. Quad means 4. And quad means 4, meaning to say it comes with 2 inputs of gates. If you ask me now, in that specification, a 7408 is basically has 4 gates inside. Next meeting, I will bring this IC, but you will not see inside the gates, right? It's already embedded there in the packaging, but the pins will help you. The pins will help you to identify which is which input should be in the gate 1, which inputs should be in the gate 2, which output should be in the gate 1 as well. Right. So there are some configuration. We call that one a schematic diagram of a pin configuration of a logic gates. But unfortunately, you will not be seeing this one in physical because you're not be performing in lab. But you will see this one in our logic simulator. We have a software to perform some of the labs, and literally you will see this kind of ICs or packaging that you will going to use in every experiments that will be working. And of course, rule of the thumb, electronics needs some power. They should be running a voltage running through on it, but a small voltage only. Basically, it's sometimes 5 volts, and it should be grounded. And for you to see the outputs of these gates, we used to put some LED or LED or light emitting diode, a very small one. It depends on the color. And we will going to use some switches or using some, what do you call this one? Connecting pins or something like that. And you can see the output. Literally, it will turn on the LED or light emitting diode, or it will off, depends on your inputs, because it depends on the expression or it depends on the inputs of your gates. You're just done with the first gate, that is AND gate. For now, this is not important. This is what you're seeing, the schematic diagram. But we will apply that one somewhere in your laboratory experiment using a simulator. But the most important is, of course, this information that holds the AND gate. The symbol, the function, expression, and the truth table. Let's move on to the second one. Excuse me, I need to answer this one. Just a sec. Did Salih Saeed, Jafali is here? Salih Saeed. I think it's not here. 1 second. Huh? Close the sharing. Just give me 1 sec. Okay, I'm sorry. I never turned off my microphone. Okay, let me just allow me to open it once again. Someone is just inquiring for the student. Okay, any questions so far? We just only had one basic gates, and that gate is of course an AND gate, right? So this time we're about to see the other basic gate, which is an OR gate. You know, the simplicity of this is if you know already the AND gate, it's like pretty much like a multiplication. The OR gate is similar to like an addition of binary. It's a function is like a binary, but not literally binary. I mean addition, because we use literally the OR operator. But if you perform, it's like addition of binary. And only, of course, the symbols will be different from that AND gate. Similarly, if you have two inputs, will come also two inputs, A and B. Output may be Y or F, it doesn't matter. But the function now is A plus B. Before it was A times B or A and B for AND gate. But this plus sign is actually, it's an OR gate or operator. Or we can read that one as A or B. Or if we convert that one into number system that we had before in chapter 1, it's like an addition of binary. That plus sign, of course. And then you can see also the truth table will also be changed because the functions change. Because the function of an OR gate is just like I said, it's an addition of binary. If you will simulate this, if you will take the input of 0, 0, or 0 or 0, or 0 plus 0 is 0, 0 or 1, or 0 plus 1 is 1, 1 or 0, or 1 plus 0 is 1. Okay, now, when it comes to 1 or 1, this is like what we had in addition. 1 plus 1 is 0 carry 1. We don't adopt that one at the moment because that is literally for arithmetic operation. But when it comes to 1 or 1, both 1 inputs are true. That only you might be having true. If you will see them in true or false equivalent, if you got one true from an OR gate, your output will be true. Except only for 0, 0, because there's no true input there. The 0, 1, just like false or true is true. So because you got one true there, or 1. True or false for 1, 0 is true. Because you have 1 there as true or 1. And true or true is both true are true. Or 1 or 1. Or true. We don't use the 0 plus 1 plus 1 is 0 carry 1. Okay? So don't misguided on that, because this is logical and operator, or logical or operator, right? You can see also the other gate now is what we call as a NOT gate. I think this is one only special gate that comes with a single input, but actually we have another one which is a buffer, but we'll just stick on this inverter. There are two names of this NOT gate. We call that one as an inverter gate as well. Normally it has one input, that's same, of course, all the gates are having single output. And assigning the inputs, it could be A, it could be any letter, but the only thing that you will notice in a NOT gate is just like a complement. And remember in chapter 1, the complement? We complement, the 0 becomes 1, the 1 becomes 0. So this is specifically the application of that. And that performs with a NOT gate, or we call from the word itself, inverter. Right? Because from the symbol itself, that there will be what do you call this one? Triangle, right? When a small buffer there on the tip. Any input are coming in will be inverted. So you can see now the simple truth table of an inverter is 0 become 1, 1 becomes 0. It depends on what variable you're saying there. In some cases, we use a Boolean expression with a bar on the top. And actually, that bar on the top of that a is what we call as, actually, that was complement. Right? Because inverting is pretty much the same as complementing when we saw the first complement and two's complements, right? So these are the three basic logic gates. So we have the AND gate, we have the inverter, and we have the OR gate. Right. There are some cases that you might be seeing some combination of those three gates. Oh, teacher, this is quite difficult now because now you're putting different gates and put them all together. Literally, actually, out of this combination, we will learn another gate out of this. This time we have three basic gates. And actually, gates is not only stopped in three gates. We still have, I think until 7, we still have other gates that we will discuss. but most of them there came from those three basic gates. And one of these one is the AND gate. This would be your fourth type of gate after you learn the AND gate, OR gate, and NOT gate. Next will be the fourth one is NAND gate. This is not basic anymore. Why? Because they are combined with two gates. And what are those gates combined? AND and NOT. That's why it came like NAND gate. The N there, the first, of course, the N there is not gate actually. No, I'm sorry, not AND gate. In short, they make it NAND or NAND. It's basically the opposite of your AND gate. What I mean to say, why opposite? You know what's the function of inverter? Whatever the output coming from a typical AND gate, it will be inverted, and that would be your final answer for your NAND gate. Hopefully you get my point. If you will see the truth table of AND gate, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. The answers are 0, 0, 0, 1. But the NAND gate equivalent, it will become 1, 1, 1, 0. Why? You can see it from here, from this truth table, that every output that coming out from the typical basic gate of AND gate.
It's converse of Y.
Yes, pretty much. But basically, you don't need to show me this combination. I just only show you the property why it became like that. Because the real symbol of a NAND gate is this on the right side. Typical AND gate with a small buffer. Buffer, that a small circle on the tip. Yeah. Only it shows that that buffer is actually a typical inverter. And this Y prime is just showing off this one because it's shows here that you have a couple of gates here. But if you have only drawn that one into a simplified one, you don't need to show me these two columns on the output. Only the 1, 1, 1, 0. So how we perform this one? 0 non-zero is 1. 1 non-zero is 1. 0 non-1 is 1, and 1 non-1 is 0. So it's opposite, directly opposite of an AND gate. But of course, if you don't understand this property, it's just only a combination of AND gate and an inverter. But the next time you will do this one, no need to show me in two sets or two different gates. Just show me this single symbol of that combinational basic gates, which is with a small buffer on the tip. Okay, that is for the NAND gate. That is for our fourth type of the gate, but only a part of this is a combination, but considering it's still a type of a gate, right? And from this slide, where is the gate? Gate is this. Where's the symbol? That one over there. Where's the function? Actually, the function is there. So y equals to A and B with a complement on the top. Remember complement? It's an inverter, right? So whichever the output of Y and B, it should be inverted. If you go back to inverter, it comes with a complement. I'll show you. There, Y equals to A complement. It comes with a bar on the top of A. Because whatever the output, you have to complement that one, which means inverted, right? 0 become 1, 1 becomes 0. Same also here. But the expression there is A and B inside. Underneath that one is A and B. But you need to complement, and that is the equivalent of your output. Right? So that's why we have here Y prime there is just like the complement of your A and B. So same also, it will just invert the output of your A and B. If we have NAND gate, we have also combination of NOT and OR. So this will gonna be the fifth one. This will gonna be your fifth type of logic gates after knowing the three basic gates. And this is quite easy as well. And definitely, it's an opposite of your OR gate. Why? Because there's a combination of OR gate and a typical inverter. You remember the OR gate truth table? 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. So which means it's 0, 1, 1, 1. So you can see now the output of opposite of NOR gate. It will become 1, 0, 0, 0 respectively. If your input is properly arranged, 0, 0, 1, 0, 0, 1, 1, 1. And ideally, the same also what we have seen on NAND gate. The functions of that one is also A or B, but there's a complement on the top. Or maybe you can say it Y prime. All right. So similarly, you don't need to show me this couple of gates if you're providing me the NOR gate. Instead, you can use only this number 3, which is OR gate with a small buffer on the tip. So that makes the equivalent of an OR gate. No need to show me in this one OR gate and one inverter. By just only showing this truth table, if you don't, that simplified gate, you don't need me to show me the 2 columns of output there. Just provide me only the final one, which is 0 nor 0 is 1. 1 nor 0 is 0. 0 nor 1 is 0. 1 nor 1 is 0. So which means it's directly opposite of OR gate. Right. Any questions? We have about to reach the 5 different types of gates. And I have need you to really understand the symbol, their functions, their expressions, and their truth table. Because individually you should know them very, very much, because the next will be, we'll put them in one logic circuit all together. And now, teacher, what will happen to the expression now? It will be now a bit longer. The Boolean expression will now becoming longer, depends on the number of gates that you're combining. So before you jump into that one, you should know first individual first. Treat them, know them much, and at least, I'm not saying memorize it, at least just once, every time you see that function, you should know how it works. You should know its equivalent expression. You should know the function. Okay, I already mentioned function, the truth table as well, right? Because if I gave you any or one of those, vice versa, you can give me what's the equivalent of that one. I think we're about to complete that part of that session. And that session is basically, it's all about giving you time for just knowing the basic and knowing also some combination out of that one. So actually from those 3 basic, we came up only with, for now, 2 combinations, AND and NOT, and OR and NOT. That makes them none and no respectively. Later a bit, we will going to have this activity in chapter 2, and we'll just hold on to that one first, and I will show it to you by next meeting. Okay. So just give me a little more time just to touch this universal gates, because this time now we know already none and we know already NOR. Because none is made up of a couple of gates, which are the NOT gate and the AND gate. Similarly to NOR gate, it's also made up of a couple of gates, which is NOT and the OR gate. Now, this now makes this gate become more universal. Why? Because we can, out of this NON and NOR gate, we can implement them in a typical gate, actually, in a typical basic gates. I think you won't not be able to understand at the moment. If I use a combination of NAND gate, I can make a basic gate out of that. But if you will see, it's very complex because you're putting all the NAND gates together. But if you check the expression, you check the Boolean functions, and the output will be matches the truth table of that basic gate. So which means universal gate doesn't mean that if I want you to apply only OR gate, can I only apply OR gate only? No. We can also use some universal gates such as NAND and NOR. I will show it to you later. We can implement them in a way that they are made up of NOR gate, but the output is a basic gate. Same also, we can make use of all NAND gates, but the output is only basic gates. Okay, we'll see that one just for a bit. This is a good example of what I'm saying as a universal gate. This definitely will come in somewhere in the short answer questions or maybe some multiple choices, but pretty much like practical, because you should know the real functions of each one of the gates, especially NAND and NOR, because NAND and NOR can be used as a universal gate. Universal meaning you can apply any circuit out of those universal. Assuming that we know already this inverter, AND gate, and OR gate, correct? You have seen that one from the first three basic gates. You have seen the symbol, you have seen the respective functions, you have even seen the respective truth tables, right? Assuming, if I ask you somewhere in the exam, that make a universal gate using this inverter, but you're gonna be using a NAND gate. No other than gates will be applied, but you will only use a NAND gate as a universal gate. Okay, now this one is quite difficult. How can I do that one, teacher? How will I know? How will I use this NAND gate? And it will perform similar with the basic gate. You know what? The technique of this is basically on expression. If you know already the function of each basic gates, we can simulate one of these. I'll show you one. In the inverter, basically it's only one input, right? The output is of course also one. And if your variable is A, it will become A complement. It's just an inverted complement, right? How are you going to apply that one using a universal gate, but it's a NAND gate? You can see here the circuit using NAND gate on the inverter. Of course, a typical NAND gate has two inputs. How can you make it one input? Right? How can you make it one input? One input will be shorted from the other input, which means I will not force to input two already inputs, because usually NAND gate comes A and B, right? So what I did is I make that second input and I top that one to be shorted, so that if I just throw an input, it will come the same on those lines. So pretty clever, right? So if I input A, and suppose I input 0, okay, let's put it in binary. If I input 0, what is this input will come in here? It will come 0, non-0. If you will check your truth table, what is the 0, non-0? That is the opposite of AND gate. It will be 0 and 0 is basically 0, but 0 non-0 will become 1. So what you have input as 0, now it became 1. That's why it's a complement there. If you're not pretty sure, try 1. From the circuit using NAND gate, I'm simulating over there. If I input 1 here in A, knowing that we have shorted those inputs that become now single inputs now, of course, if I input 1, that 2 inputs will become 1. So it will come 1, non-1. If you want to check your truth table, what is 1, non-1? That is 0. So your 1 become now a 0. So we're very sure now that this circuit is the same like an inverter that it used to be. But only the difference is it uses a NAND gate universal. Right. Maybe this is easy for one gate only. But what if we have now an AND gate? Let's review what is the function of AND gate. It's pretty much multiplication, and of course we have a couple of inputs there, and any multiplier of 0 is 0 basically. So 0 and 0 0, 0 and 1 0, 1 and 0 0, 1 1, 1 and 1 is 1. But you will going to implement it using NOT gate only. And how you can do that one? There's a small magic here that since you have already knew that the inverter works like an a single input of NAND will come as an inverter. Why not do two sets of NAND gates? Two sets of NAND gates. You know already the functions of NAND, since this is what we have told, we have to use NAND universal. And if you assume that suppose 0 NAND 0 is equivalent to 1, and that one is y prime, huh? That one will come in like an inverter, will straight input those input that you shorted, 1, 1, and 1 and 1 will become what? 1 and 1, oh, that is 1 and 1 is considered as 1, but 1 non-1 will become 0. So see, 0 and 0 will be input in the non-equivalent gates must be 0, which is the same also with AND gate, a typical AND gate. If 0 and 0 is 0, in the universal, it will come also 0. You still have 3 more combinations. If you're not sure, try the 0, 1. You're not sure, try the 1, 0. If you're not sure, try the 1, 1. And I know it's quite difficult. And what if I draw like this to you? So that you will understand what I mean to say. I will draw this logical and non-universal gates. Oops, I don't have symbol like this. Or maybe I will just copy this one then. We'll just copy this one. Capture the screen. And I'll just paste it over here. Yes. I will just copy this part. I'll make it another one because it's quite difficult if you're not in the board, no? Okay, I'll just make like this. Okay, but I need to remove this one so that you'll not be confused. Right. Okay, assuming A and B. Okay, look at this. I will just make a scribble, huh? You know already the function of AND gate. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. Remember, I simulated using 0, 0. Oops. Let me just increase the size. This is 0, 0. All right. We are expecting it must be 0 also. But we'll see if it works the same as an AND gate. The 0 and 0, non-0, will become 1 here. Because that is the truth table based on that function of NAND gate. It's a reverse, it's the opposite of your AND gate. Because in AND gate, 0 and 0 is 0. But in NAND gate, 0, non-0 is 1. Now remember, this is an inverter, right? So whatever it came here, it's also 1. This is also 1 because you short that input. Okay, now what is the equivalent of 1 non-1? It will be 0. But without that inverter, of course, the 1 and 1 in AND gate is 1, but 1 non-1 is 0. Now it's the same output that came out from your typical AND gate. 0 and 0 is 0. Okay, if you're not sure again, let's try 0, 1. What is the equivalent of 0, 1 in a typical AND gate? 0 and 0 is 0. Well, let's see now from your universal, what do you call this one? Universal NAND gate that works like an AND gate. What is the equivalent of 0 non-0? You can check it out, the truth table, if you haven't figured it out. But just remember that is the opposite of 0 and 1, it's 0. But this will become 1 because this is none. And now this is, of course, both of these will become 1 because it's just like an inverter equivalent. 1, non-1 will become equal to what? 0. So now, it's the same like your typical AND gate. 0 and 0. 0 and 1 is 0. Okay, maybe one more. Let me jump into 1, 1. 1, 1. What is 1 and 1 in a typical AND gate? 1. Right? This must be also
Is
becoming
1, but now
yes.
it will come 0, I think.
We'll see, because it should come the same. If this will come 0, this is wrong, by the way. The 1 and 1, the 1 and 1 is in AND gate is 1, but this is considered universal NAND gate. It should be 1 also. We'll see, inshallah. What is the 1 non-1 equivalent? 1 and 1 is 0, but this is none. 1 and 1 is 1, but this is none. This is 0. If you're not pretty sure what I'm saying, go back to this, because all the things that I'm mentioning is all about equivalence combination. See, 1 non-1 is 0. Here, the last one, the last row. 1 non-1 is 0. That's why I make it 0. Now, this, of course, it's a shorted one. So this will be 0 and 0. Go back to the truth table. What is a 0, non-0? It's 1. So which means the same as your AND gate. So it's correct. It's not 0 there. So which means this one are basically equivalent. Oops, I'm sorry. This one are basically equivalents of the respective basic gates. But what I have only asked you to do, use the use the universal NAND gate. No other than NAND gate, no other than gate, but just only NAND gate. So you try that one also in OR gate, and there will be a cascaded 3 NAND gates universal there. And you can see that each one of those gates have been shorted because we need only 2 inputs, right? And at the end of that one, it should matches on the truth table of a typical OR gate. Right? So quite interesting, but if you don't understand the functions of a typical NAND gate only, NAND gate and NOR gate, you won't be able to understand this one, right? Because we know already the basic. These are the 3 basics. We only do different gate, but their output are the same. That's why universal gates. If we can do that one in NAND gate, of course, we can also do that one in NOR gate. Right. So which means these are the typical OR gate, 3 basic gates. They should perform same, but with the use of universal gates. Maybe before we end up our class, I'll just grab one of these. Maybe I will take, you want this one, the hardest one, this 3 NOR gate. Okay, let me draw that one and, no need to draw. Let me just capture them and then I will copy paste it only. So that you know that really works the same. We're not just giving you those, but you have to also to check whether all those theory behind it should be correct. Because if you don't understand how you simulate it, what you're doing is just you're memorizing it. Okay, let me just remove this excess there so that you'll not be confused. All right. Okay, review. We will now have an equivalent NOR gate, but this one should work as an AND gate. See, it's there. Okay, now you know already the truth table of AND gate. 0 and 0 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 1 is 1. Only 1 will be there if 1 and 1. So 0, 0, 0, 1. Let's see how it goes here. Maybe we'll try 3 inputs. 0, 0, 1, 0, and 1, 1. Okay? Let's start with 0, 0. 0, 0. Right. Now, please review also the truth table of NOR gate, because you may be confused what is the truth table of NOR gate. It was here, I think. Yeah. 0 nor 0 is 1. 1 nor 0 is 0. 0 nor 1 is 0, and 1 nor 1 is 0. So reverse, 1, 0, 0, 0. Okay, at least you know how we simulate this. So since we shorted these pins, it will come now one input. So whatever we input here, it will become both 0. Oh, what is 0 nor 0? That is equivalent to 1. I'll show you. 0 nor 0 equals to 1. Last column. Because I said this is directly opposite of OR gate. 0 or 0 is 0, but this is 0 nor 0. That's why it's 1. So same also here. 0 nor 0 is 1. Okay, so what is 1 nor 1? In 1 or 1 is 1. But in 1 nor 1 will become 0. So which means I think it's matches now. Okay, again, 1 nor 1 is 0 there. Right, that's why it's 0. So the 0 and 0 is the same with this first input that we did, which is equivalent NOR universal. Okay, let's have another input. Let's make this one instead of 0, 1, I'll make it 1, 0. And the other one later we will do 1, 1. Let's try 1, 0, combination. So we know that this is already the same input. What is 1 nor 1? 1 nor 1 is of course reverse of 1 and 1 or 1. So this would be 0. This would be 0. What is 0 nor 0? Okay, maybe if you don't see it, it's here. 0 nor 0 is 1. 1 nor 1 is 0. So this is 1. Right? Okay, now this time we are about to complete now by just simplifying this last part. 0 nor 1. Okay, here, 0 nor 1 is 0. So which means this is 0. Now, can you check what is 1 and 0 in a typical AND gate? Is also 0. The same. Okay, maybe one last input we try is 1, 1. What is equivalent 1, 1 in your AND gate? 1 and 1 is 1, right? So we should be expecting 1 here. But this is all universal NOR gate. So let's try this one. This would be 1, 1, of course. 1 nor 1. 1 nor 1 is 0. 1 nor 1 is 0. 0 nor 0 is 1, which is all it matches, except only for the 0, 1. I did not check, but definitely it will match. So which means that this universal NOR gate is equivalent also with a typical AND gate. You can just understand that one by just simulating it by yourself. Don't just memorize this. You know already the pattern, but the most effective way basically is what I'm showing it to you. I'm simulating it means I'm really literally manually entering those inputs, and each one of those binary bits should simulate by knowing the inputs and outputs based on their functions, and come up with the functions, a total final answer for that one, right? So which means these gates are basically very useful because they call themselves as universal. Only those between NOR and NAND gate can make them a difference, right? But I know it's a bit complex because why should I use this one, teacher? Because we have AND gate anyhow. Why are we going to use this? And as a matter of fact, you're not optimizing your logic circuit, which is true, because less gate is much more optimized and much more better. Only the thing is maybe if AND gate is not available, at least we have this bunch of NOR gates ICs. We can make an equivalent of these basic gates. But tell you frankly, yes, it's not optimized showing this number of gates. More gates, more kind of power needed, more expenses because you need to have those more ICs as well. And sometimes in the speed, maybe it might much more faster in a simplified one. But only, of course, for the purpose of learning the expressions. And this makes sense. At least we know and we have an idea that we can also use an equivalent universal gates, nor and none, with the use of this equivalent basic gates. Okay, so I will stop there at the moment. So equivalent gates will later be having some buffer, so that will not be confused. So we're gonna be overloaded with with this information. So I better yet stop there for a while, and may ask you if you have some questions. So let me just turn off now the recording.